All right, so welcome back. Welcome back to this. Welcome back to this channel for another video, yet another video, and I'm telling you this might be like your introduction to building transformers, building language models. I think so. This video, like if you go to, I think if you go to any person and probably at the end of this decade, maybe this decade 2030, and if you ask any person, then I think and if you ask a person that what is the best, the most complicated and the best invention of this whole decade, then the answer will probably be chat gpt and language models. Like the hype is real. There has been a lot of hype around this field now. Like if you look at chat gpt and all that, it's because the like the ability of computers to understand text, to be actually finally able to really understand what is the science behind text, right? How we can talk and to be able to understand different types of text and to be able to actually generate like hundreds of um, lines of text. That is like talk like us. That is the field we are going into right now. So we are going to learn about transformers. So what is transformer? And the most revolutionary paper in the field of deep learning, probably the most revolutionary, probably the best paper. And sometimes people do fear reading this paper because it does it is very hard to read in terms of paper. I don't think it is very easy to understand. It is actually very hard to understand to actually read this paper. But there are some people who have already read it, and there are many blogs and all that. So make sure to check out. There is a wonderful blog. I'll just put it in the link in the description. Make sure to uh, check that out also. So this is the paper. Attention is all you need. So the classic paper by Google. Some great people at Google. Some very smart people at Google wrote this paper, I think. And then I think I recognize this person. I don't actually know him, but I think he teaches the natural language specialization in deep learning AI, Coursera. Anyway, so let's get into this paper. What this paper is all about. So yeah, this paper is actually meant to solve a problem. So like it is not exactly a problem, but it's just a improvement to this previous language models that we have built. And in the last video, I've told you about word embeddings, of how we can actually represent text, and how we can actually uh, put in or make the computer understand the meaning of that particular word. We have understand how to represent text. So after we have used word embeddings, we could be able to use RNNs and LSTMs or GRUs to be actually model this text, to be able to actually generate new text in terms of actually word embeddings, or just classification, just selecting the next word out of the corpus given the previous words. So we could do that. We could just use an RN or an LSTM or GRUs. But the problem that we are facing, or not the problem, but the way we could solve this problem better, is by actually finding a way such that there is relationships between these words. Like that is probably like, if you look at the NLP research that has been happening since the beginning, since the development of RNNs and all that, they have figured out, the researchers have figured out, even I have, when I was building some projects, back in the old days, when I was developing my projects, I figured out that the most important thing is to teach a machine learning model to be able to understand the relationships between words, and to be able to understand which word should the model give more importance to. That is one problem that we are solving. The problem is to be able to understand what is the important words and what is not. What should the attention be on. That is why the paper, the name, hence attention. So another problem is that RNNs or LSTMs are not meant for parallelization. Like you have to do, you cannot carry the process all at a time. First, you have to input for the first state and state, then for the next state and state, and all that. So it is a very risky process, and we cannot use the powers of GPUs. We have very powerful GPUs nowadays. NVIDIA RTX 4090 came up, all the hype about for RTX 4090. So there are powerful GPUs, but these RNNs and LSTMs and GRUs are not able to use the power of this GRS as these GPUs, as because there is no parallel computation, right? So there is like a one after another approach which does not use the power of GPU. So we need to do some types of parallelization to be parallelization, right? To be actually, rather than using a sequential model, we should somehow make it like a neural network, right? So that is the problem. So that is the problem that the Prapor is solving. That is the problems with the previous models such as RNN and LSTMs and GRUs. So now if you just we can just read the background. I think I haven't read this. Probably, you know, probably why they do transform and all that. But like the vocabulary, probably they should they have done a PhD in English or something. It is actually very hard to understand the English. So this is the famous diagram. This is the most important probability diagram. In this video, as I've told you, we are going to look at this encoder. So how we are actually able to understand the input sentence. So like for almost like for some problems, right? For some problems, you'll have an input and you'll have an output. In terms of NLPs, you'll have some input. Let's say question answering bots. You have a question and you have the answer. So let's say you have let's say you have a chat bot. You'll get the input as the question. So encoder is all about understanding these inputs, and like let me tell you something. Encoder, like what this function of this encoder is not actually to predict an output, but to actually add some more important things, important features to this embeddings, right? So we have embeddings that represent these words, and then we'll just add this other values or some features that can be helpful for the model to be able to actually generate human-like text, to be able to understand what is important text and what is not important words, by the way, right? So that is the thing. So we'll have encoder and a decoder part. So encoder is nothing but we'll get the input embedding. So this is the inputs. We'll do embeddings. I've told you about embeddings in the last video. We'll get the input embeddings. We'll add something called positional encoding. I'll just talk to you about that now. What is positional encoding is? It is just nothing but we'll just add positional features. In the case of RNN, you do have the positional features, what is first and what is not. But now what we are going to do is, based on the index, we are going to add some positional values using some sine and cosine functions. And then after we get the output, we'll get the change output by adding the positional encoding. We'll get a we'll get to know the information of position of each word, right? So we are going to have input embeddings. For each word, we are going to have separate embeddings. So we'll get a matrix of matrix, right? And then we are going to do an operation called multi-head attention, which is actually the main part in the attention mechanism. We'll do something called multi-head attention. I'll tell you about that. And look out, we also have this residual connections. So we are going to get this input, right? And then add it after multi-head attention, just to make sure that we don't fall into the problem of vanishing gradients. That's why resonate came hand in hand. So we'll first perform multi-head attention. We'll add the previous layer, add the input. Again, we'll do normalization. We'll do a feed forward network, and also we have another residual connection, and we'll finally get the output for the decoder. That is idea. So first let's talk about multi-head attention. What multi-head attention actually is. So I'll just go through the whiteboard. Reading paper, when you are especially learning about multi-head attention, reading the paper is not a very good idea. So I'll just write something. Good. So yeah. So the idea is we'll have three vectors. Normally they call them query, key, and value, but I don't think we should actually remember that they are key, like query, key, and value vectors, because they are as they are found by the optimization process. We cannot actually determine what the computer finds useful. So we'll just have this simple formula. I'm just going to write out the formula. Don't like even if you have any doubts like why do we write this formula, I'll just explain it to you in just a minute. So what we'll do is we'll calculate q. So we'll actually calculate q, which is actually equal to wq multiplied by x. We'll have k, which is equal to wk multiply that by x. V is equal to wv multiply that by x. So I'll just wait. Yeah, sorry for that. Okay, so we'll calculate q, k, and v vectors, which are actually weights. We'll multiply weights by x. This is x, by the way. So we'll have x, and we will multiply that by some weight matrices. WQ, WK, and WV. And after we have calculated this q, k, and v vectors, query key and value vectors, we'll actually do something called we actually for each word. So let's say we have some words. Let's say I say my name is Joel. So let's say this is the input encoding input sentence. I should say. I'll just first tell you what will happen. So let's say my name is Joel. Control minus V. Yeah. So my name is Joel. Let's say what will be the output of this multi-head attention is we are just going to create some numbers. Let's say. Okay. So I'm just going to draw boxes now. So let's say this is high. This is going to be higher. Let's say this is it's a little lower. Say a little more lower. See this is more lower. So I'm just going to explain you what is going to happen. What is this? I'm just going to draw some boxes. This will be higher. So by now you might have already understand what is happening. What is happening? Little lower. Little higher maybe. See very lot higher. And little lower. Lower, higher, lower, higher. So as you can see here, what we are creating is the darkness, the thickness of this box, the thickness of color of this box determines the higher value, by the way. So what we are going to do is for each word, right? So for each word, like let's say for the word my, we are going to calculate all. So for this word my, we are going to calculate the relation or the attention it has to give for each word. So let's say my and my, both my and my has higher values. As you can see, my and name has a little lower value. My and is has another low, some more lower value, and my and Joel has a little higher value. So that is why we are going to have some, like these are all figured out by the model by the process of optimization. We're going to make the model find this the intensity. So we'll just look at the formula how to calculate the intensity. We have already got the q, k, and v vectors. Now let's calculate the actual formula. So it's going to be equal to we are going to multiply q multiplied by k transpose, and we are going to do something on k. We are going to transpose it into -2, -3. I'm just going to tell that why we do it, and then we'll perform the soft max. Right, so we'll do soft max. I'm just going to say soft. We're going to perform the soft max, and then we are going to divide that by the square root of like I'm just going to tell that again. So we are going to perform soft max, and then finally we are going to multiply that by v. So v is actually the value vector. So what are we doing here? We are multiplying q by k, right? And then we also multiply that by v. Wait a minute. Right. Sorry for that again. So we are, let's say we have three words. Let's say we have three words. So what we are going to do is for q1, let's say we have q1 for the first word, the query vector for the first word. And first we are going to calculate the query vector of q1 times k1, the first query vector multiplied by the first key vector. And then we are going to do this by v1, and then we are going to do this for v2, k2, and v2. So what are we going to do is we are going to calculate. I'm just going to go up a little bit, or a little bit minus. So for the word my, right? So for the word my, we are going to have a query vector. So what we are going to do is we are going to multiply the query vector of my by the value vector of my. So we are going to have a higher value because both of the values of it are equal. So remember, in matrix multiplication, similar matrices will have higher values. So therefore, darkest box. And then we're going to perform that this operation for k2, which is name, right? So we're going to multiply query 1, which is the actual word that we are caring about, that we are calculating now, and we are going to multiply that by k2, determining how similar or how important should we give for this word name. We are going to multiply that by k2 because k2 is nothing but the key vector of name. And then we are going to do that same for everything. So we are also going to do with name. So we are going to say q2 times q1, sorry, k1, q2 times k2 and all that. We are going to do everything. So we are going to essentially calculating for every box. So every box will have this some type of formula, and these 1 and 2s will change. So these indexes will change, and then we are, for every query vector, we are going to multiply the one query vector with all the key vectors and value vectors. Hope you understand what's happening. It's very simple. This, if you want to understand why we use this formula, well, we use it to actually determine how similar both words are, or how similar does the model think both the words are, or how important should we give for a particular word. And again, remember, this weights will be optimized. So therefore, these values will be changing, and hopefully when we train our model better, hopefully we'll get a graph something like this, hopefully representing the actual thing, right? So therefore, we are going to have this vector as output. So that is multi-head attention. We are going to perform this. Sorry, this is single-headed attention. So we have calculated Q, K, and V. So all of this process, right? Yeah, control minus V. So all of this process is, we are going to carry it out for, let's say, 4 times. So what we are going to do is, rather than having Q, K, and V as a single, rather than having one table, we are going to have multiple tables. Right? So rather than having one table like this, we're going to have multiple tables, and hence we're going to have different matrix of matrices. So therefore, we would have a complicated output given by all of these matrices. So each head will get you an output, right? So each will get you a embedding like this. We are going to get a new vectors for each word and for every word. So we'll get this output for, let's say, 4 heads, or 4 tables like that. So that is the idea. That is the idea of multi-head attention, to be able to actually use it. Now you can see what is happening. We're going to do some softmax and all that. You can see here, we'll do matrix multiplication, and we'll use softmax, and then we'll finally do matrix multiplication with V. That is scale dot product attention. Multi-headed attention is nothing but we'll have H number of scaled product attention. I hope you got what is happening here. As you can just look at the formulas here, right? Yeah, and then we are going to concatenate all of these heads. So like one table, as I've told you, is of only like one head. So wait a minute, my laptop's is charging is less. I'm going to just charge it and come back. All right, sorry for that problem. Yeah, it is charging. Yeah, I think it is charging. So yeah, the idea is we'll just concatenate all of these heads and multiply, but by further another matrix. So yeah, there is a lot of matrix multiplication, and then we'll further multiply that by W0, which is another weight vector. So we'll just concatenate. We'll just combine all of these heads and multiply that by W0. That is the idea. Then positional wise field farming, I also already told about that. Yeah, the positional wise field farming network is nothing but that's a normal feed forward neural network. We're going to use a ReLU function. So max 0 and this is nothing but the very ReLU function, and we are going to have, let's say, 2 layers, right? And then and there is something else. Why self attention? Why should we use self attention? You can just read it now, or you can just read it. I'll put the link in the description of the paper. Make sure to just read it. Make sure to have a dictionary aside. or good. So that is the idea. This paper is considered pretty hard to understand, but really huge thanks to all of these people who have explained it further, and like all days it has helped me in all days. So that is why I mean, good paper, good research, and even the chat GPT that you saw uses this transformer. This is actually transformer that is this idea. I think this paper is released at it is very old paper, like not very old but very old paper. 2017, I think. 2017, pretty old, but still this paper is like very very revolutionary. And the transformer models, like even chat GPT has the same architecture but with more parameters. That like there are more attention heads and more parameters. Like there are more there are almost like I think 100 billion parameters, probably more than that. That is the idea of chat GPT. As there is you know ability for them to actually train huge like use huge GPUs, they can actually develop a sophisticated architecture model like ChatGPT. So that is the idea. Now let's I'll just go through some code. I'll probably put it on GitHub. I'll give you the link in the description. So make sure to check that out. So this is the code for doing the transformer encoder, building the transformer encoder. First, we'll have a function scale.product, the same function that I've told you. So we are going to get this Q, and then so we are going to get this Q, K, and V, as you can see what we are, and then we are going to get the size as the DK. I forgot to mention we are also going to divide the scale product multiplication of Q, K, and V by square root of DK, right? And then yes, we'll first multiply Q and K, right? We are going to multiply Q and K, and then we're going to divide that by square root of DK. And then we're also going to add attention. We are going to calculate softmax. We are going to calculate the softmax of scale, and then we are going to finally multiply that by V. And then we are going to do multi-head attention, which is nothing but we have this we'll have this QKV layer. So remember, we have this QK and QKV vectors, right? In like when we are implementing in TensorFlow, like from scratch, we actually use a dense layer. That is actually, and like you calculate QK and V vectors all at a time and update all at a time. So that is the idea. First we'll calculate QKV layer vector, which is nothing but 3 into D model, and then that. And then we're going to have an output D model, right? We are going to extract QK and V from that, right? We are going to extract QK and V from this huge matrix, and then we are going to calculate everything. So we are going to calculate everything at a time. So we are going to do the dense at a time, the linear layer at a time. And then we have this layer normalization. You know about normalization, right? I already told you about that. Subtracting the mean and dividing by the standard deviation, right? To actually normalize the data. And then we have this positional wise feed forward network, just a classic dense layer. We'll do a dense layer. And then we'll build the final class of encoder, right? So as you can see here, we'll perform the multi-head attention, normalization, dropout. I don't think we haven't used residual. We have used residual here. Now we'll just do some initializations here. We'll do the residual network. And our final network is ready. Therefore, this is the basic implementation, and actually not pretty complex. The basic idea is actually having this QK and V vectors, and actually finding the importance of each word for each. Like we are going to find the attention each word has to give for each of this for the other words in this in the input sentence. So all this attention is going to happen between this input sentence. So by this encoder, so the reason for using this encoder is, by using this encoder, we could actually able to understand each words better of the input sentence. So to actually understand the input sentence, we use this attention mechanism. So, sorry, the encoder of the transformer. So that is the encoder. Thank you for watching this video. Right, I'll put this code and end this paper in this description. So make sure to check that out too. So thank you for watching, and I'll see you in the next video.